Hello everyone. Today we are presenting our project on the RSA digital signature implementation, which focus on securing communication using cryptographic techniques. In today's digital world, sensitive information like banking data, emails and documents are constantly being transmitted over networks. This makes security extremely important. Our project demonstrates how RSA digital signature can be used to ensure that messages are both authentic and secure. This work is part of our cryptographic and network security course, and through this project, we have implemented and analyzed the complete process of digital signature generation and verification. Now, we will begin by understanding the core security objectives behind this system. In any secure communication system, three important objectives must be achieved. The first is authentication, which ensures that the message is sent by the sender and not by any attacker. The second is integrity, which ensures that message has been modified during transmission. Even a small change should be detectable. The third is non-repudiation, which means the sender cannot deny sending the message later, since the signature is uniquely tied to their private key. In our implementation, we use the RSA algorithm to achieve all these three objectives using public and private key cryptography.
Now let's look at how RSA key generation works in our implementation. We use the PyCryptodome library to generate RSA keys securely. In our code, we generate a 2042-bit key which is considered secure for modern applications. This process internally selects large prime numbers and performs mathematical operations to generate two keys, a public key which is shared openly and a private key which is kept secret by the sender. These two keys are mathematically related, but it is computationally infeasible to derive the private key from the public key. This key pair forms the foundation of the RSA digital signature process. Now that we have the keys, we move on to the hashing the message. Before we sign the message, we first convert it into hash using SHA-256 algorithm. Hashing is important because instead of signing the entire message, we sign a fixed length representation of it. In our code, we use SHA-256, which produces a 256-bit hash value. This hash acts like a digital fingerprint of the message. One key property of hashing is that even the smallest change in the input, such as changing one character, results in a completely different hash output. This ensures strong data integrity. In our implementation, we apply SHA-256 to the encoded message to generate this hash, which is then used for signing. Now we move on to digital signing process.
Digital signing. In this step, we generate a digital signature. Instead of signing the full message, we sign the hash of the message using the sender's private key. In our code, this is done using PKCS115 module, which implements the RSA signing standard. The private key is used to encrypt the hash, producing the digital signature. This signature is unique to both the message, the sender's private key. This means that no one can else generate the same signature without access to the private key of the sender. The signature is then sent along with the original message to the receiver. Now let's see how the receiver verifies this message. Signature verification. Now we see the verification process. The receiver first computes the hash of the received message using the same SHA-256 algorithm. Then the receiver uses the sender's public key to verify the signature. In our code, this is done using verification function that checks whether the decrypted signature matches the computed hash. We use try-catch block. If the verification succeeds, the signature is valid. If it fails, an exemption is thrown. The signature is marked as invalid. If both hash values matches, it confirms that the message has been not altered and the sender is authentic. Now let's see the demonstration of the project.
Is coming to the tampering demo. In this step, we demonstrate how RSA detects tampering. We slightly modify the original message. When the original message is transfer $1,000 and the tampered message is transfer $9,000. Even though the change is very small, the hash of the message becomes completely different. When we attempt to verify the signature using the tampered message, it shows the computed hash does not match the original signed hash. The verification fails and the output clearly shows signature is invalid. This proves that RSA digital signatures are highly sensitive to changes and can effectively detect tampering. Now coming to the conclusion part. To conclude, our implementation demonstrates how RSA digital signature provides secure communication. We successfully implemented key generation, message hashing, digital signing, signature verification, tampering detection. Through this, we ensured data integrity, authentication, and non-repudiation. These features are essential in real-world systems such as online banking, secure emails, and digital certificates. This project helped us understand both the theoretical and practical aspects of cryptography. Thank you.